One, we meet again, um, and as you can see, today we're starting on Newton's laws. I've honestly been looking forward so much to starting this section. So let's get right into it. Remember, you can reach me on my email. Okay, I'll just write my email address right here. That's Mlungisi, Mlungisi dot Nkosi at gmail.com. All right, you can reach me on my email address. That's my email address right there. In case you've got any questions. But yeah, so I wanted just to start on Newton's laws, but I don't want to go quite extensively on the theory part of it. Okay, so we know that Newton's laws, I'm only going to be covering laws of motion for now, and then we're going to have a just another video. So I'm not going to finish everything on Newton's laws, so probably I'll take this in chunk sizes so that we can just cover enough content for you to get the idea of what we're doing. And then I think the last part, we will be looking at Newton's law of gravity of mass attraction. Okay, that's Newton's law of universal gravitation. Okay, so yeah, let's get right into it. Okay, so first of all, we've got three of Newton's laws. Okay, we've got the first law. All right, the first law. So Newton's first law simply tells us that a body will remain at rest or in constant motion in a straight line unless it is acted upon by an unbalanced set of forces, okay, or it is acted upon by a resultant force. So Newton's first law, essentially what it does is that it tells us about what happens to a body, okay, in the absence of a resultant force. We'll talk about a resultant force in a few, right? So in the absence of a resultant force, if you had a body that was stationary, okay, whatever that body is, a body of mass that was stationary, Newton's laws simply say, okay, assume that for argument's sake, it's on the ground. So if it's on the ground, so what are the forces that are acting on it? You know, definitely there'd be a gravitational force that acts on it, or you can call that the weight. Okay, so or the weight of the object. Okay, weight, right? And obviously you would also have the normal force, right? The normal force. Now, what is the normal force? Okay, it's a force that acts on an object when it's on a surface, and that force is always perpendicular to the surface. Okay, so if you're looking at this, the normal force, imagine this body is pushing down, the earth is pulling it down towards its center, but the ground is also now exerting a force back up. Okay, and that force we'll call the normal force. So we say it's a force or a component of a force which is in with which it is in contact rather, and it's always perpendicular to the surface. Okay, right. So if you think about those two forces, I didn't really do justice in my free body diagram. So if you think about those two forces, this body, it's not like when it's stationary, there are no forces that are acting on it, right? It just simply means that these two forces that are acting on it as it is stationary are simply balanced. Okay, so now what does that mean when we say that it is balanced? So it means that the net force is equal to 0. Okay, so it means there is no net force, there are no net forces acting on the body. Or if you remember, we used to talk about forces that are in equilibrium, right? So Newton's first law simply states, in the absence of a net force, if this body was stationary, it will remain stationary. Okay, right. So, but if this body was moving, right, it will move with a constant speed. So I want you to please just grab something quickly. All right. What this simply means is that every time we know, or every time they tell us about something that is stationary, right? So we simply would know that the net force is equal to 0. You must just keep that in mind. Or if they tell us about something that is moving at a constant speed, okay? So it's moving at a constant speed. So what does that tell us? It tells us that there is no change in the motion. Okay, so as a result, I want you to always trace it back to this. It means that the net force is what? Is 0. Okay, so as a result, Newton's first law. Now, the application of Newton's first law, if you think about it, to talk about the law of inertia. All right, inertia. So it's the resistance of a body to a change in either its state of rest or motion. Now, if you think about it, the application where we use Newton's first law. So imagine someone was moving, is inside a car, all right, and they are moving inside a car. So what happens? Remember that both the car and the person or the passengers that are inside are also moving at the same speed as the car, right? Now think about this. So what happens if, let's say the driver sees a hazard on the road and slams on the brakes, right? So quickly, what will happen to the people inside? When he slams on the brake, the people inside sort of kind of lean forward. Okay, so it's almost like the car is kind of pushing you forward. But in actual fact, what's happening, it's the principle of inertia. It's the law of inertia. What's simply happening is that, remember, as the car was moving, so were the passengers inside. Now, when the car suddenly stops, or when it reduces velocity, Newton's first law says a body will remain at rest or in constant motion. Your body still wants to maintain the same motion as it did before, right? And so that's why when the car stops, right, your body still wants to continue moving forward, and that's why you end up leaning forward. And that's the reason, ladies and gents, we then use seat belts, right? It's to prevent against the inertia of a body. Or if you think about it, if this body was at rest, right? What happens to you when a car starts moving when it was at rest? Your body kind of leans back, isn't it? Right, but it's not your body leaning back, it's your body resisting. Remember we said inertia is a resistance in the change, right? Your body is resisting a change in its state of rest in that particular case. So if you are at rest, your body simply says, I still want to remain at rest forever and forever and forever, right? So therefore it will resist a change in its state of rest. Okay, if you are in motion, your body simply says, I still want to remain in constant motion. So as a result, when you brake, when the car brakes, all right, the body still wants to say, hey, I was moving, so I want to keep moving. So as a result, that is why your body kind of leans forward. Okay, so that's the application of Newton's first law. Okay, so yeah, so if you think about it, seat belts are used exactly for that particular reason. And if you know, for those of you who use taxis, you'll remember that there were these foldable seats on taxis back in the days. Okay, I'm sure there are still some taxis that still have those. So on the, why did they stop the manufacturing of those foldable seats, or making taxis that have these foldable seats? Because first of all, these seats were quite small, right? So they wouldn't cover your entire back. So when your body experiences inertia, then it tends to affect your body over time. So they are really a hazard. But all of that, that's a part of Newton's first law. Now, let's now talk about the second law, and that's where we're going to be spending a lot of our time. Now, please remember, on the first law, we said what simply tends to happen is that we are simply talking about this law in the absence of a resultant force. We are talking about this law in the absence of a net force. In the absence of a net force, it means a body will remain at rest if it was at rest, or if it was in motion, it will retain its motion, its constant motion, in a straight line, by the way. And the straight line part simply tells us about, you know, when a car is turning, your body kind of leans on the one side where it's turning towards. So what's happening? It's your body still wanting to maintain a straight line, a particular motion, right? So if you think about it, if a car is turning that way, your body still wants, it kind of leans over to this side, okay? So your body still wants to go in the original direction in which it was moving at. So all I'm simply saying, Newton's first law has to do with the absence of a net force. So in the absence of a net force, body remains at rest. In the absence of a net force, a body continues in constant motion in a straight line. Okay, right. Now, Newton's second law kind of picks up from where Newton's first law leaves the equation, right? Or leaves the scene, rather, right? So Newton's second law just simply says, now what happens when there is a net force? Remember, now we know what happens when there's no net force, right? Okay, or when there's no resultant force. But now, when there is a resultant force, a body will now change motion. You remember it was at constant motion when there was no resultant force, right? So when there is a net force, a body will now change in its state of motion. Either one of two things will happen, right? Either that net force causes the body to slow down, right, if it's opposing the motion, or that net force causes the body to speed up, okay? And all of that, we refer to it as acceleration, okay? Now, this is what Newton's second law states. It says if a net force acts on a body, the body will accelerate in the direction of the net force, right? And that acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Now, please remember, it says if a net force acts on a body, the body will accelerate in the direction of the net force, right? And that acceleration, well, first of all, that acceleration, is directly proportional to the net force. Now, let's talk about that a little bit, okay? And inversely proportional to the mass of the object. So we say that acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Now, there's another easier way of stating Newton's second law. It simply says resultant force or net force is equal to, or the net force acting on an object is equal to the rate of change of the body's momentum. So it means resultant force, so F net is equal to the rate. Every time you say rate, that's division by time, right? So that's division by time, the rate of change of what? Of momentum. I'm sure some of you can see this. This is where we actually derive our impulse momentum equation, right? So F net, if you think about what momentum is, that's mass multiplied by the change in velocity. Remember, that's the change in momentum, right? And divide all of that by time. If you rearrange that, now you get F net. If you cross multiply F net times delta T, okay, which is M delta V. In actual fact, this is the original derivation from Newton on Newton's second law. Right, now, if you think about it, this is where now, you remember that change in velocity divided by change in time? That's where we get acceleration, okay? Right, so that's acceleration. Acceleration is change in velocity over change in time. That's why F net will be equal to ma. Now, in this case, we say that acceleration is directly proportional to the net force, meaning, right, the greater the net force, the greater the acceleration, okay? Now it makes sense. Let's say we were pulling this car, you know, of course, we've eaten some oats and you know, we've got all the strength in the world, right? We're feeling like super beings. So suppose we're pushing or pulling this car, and in this case, let's say if I was pushing alone, all right, and I'm able to cause the car to move, I'd have to be very strong to do that. So I'm causing the car to move. If someone else comes and pushes with me, so what are they doing? They are increasing the net force. So what happens when someone comes and assists me, right? Of course, it will make the car to move even faster, okay? Right, so in this case, all it's simply saying is that the bigger the net force. You remember when I told you about graphs, okay? If you haven't watched my video on the graphs on projectile motion, I said to you, when you have a direct proportion, all it simply means is that when I increase on the one side, we always read it from the right hand side. So when I increase my net force, it will simply increase the acceleration, okay? Right, so if I increase the net force, the acceleration increases. All right, now if we look at the other one, this simply says acceleration is inversely proportional to the mass of the object. You know, this is a very good illustration on space exploration. You know, last night I was actually watching one of the rockets being launched, right? And you'll see that there are actually two parts to the rocket. I don't know the exact names, but you've got this bottom part that's full of fuel, right? And then what happens is that it launches, right? But at a point, then this part comes separates from this portion that they call the capsule, right? And in this case, if you think about it, what happens when they separate? Okay, this guy would actually now begin to move even faster, right? And the reason for that is that, now think about it. When we decrease the mass of an object, okay, suppose there were people inside this car when we were pushing it, right? Okay, and I'm pushing there alone, but now the people decide, he's struggling, so let's get off the car, right? Remember, I'd still be using the same amount of strength, but what would tend to happen to the car? The car would move faster. Why? Because there's less load, right? So if you decrease the mass, what it does is that it will increase the acceleration, okay? Right? Of course, this is on condition that the same force is still maintained. Now, putting all of this together, this is where now we said F net is equal to ma. Now notice we just rearranged this. So if you wanted to, you could have just simply said a is equals to F net over m. Okay, right. So in this case, we're putting an equal sign there. We're saying if your mass is constant, right, acceleration is directly proportional to the net force. If the net force is constant, that is, then acceleration is inversely proportional to the mass. So what we're going to do today is that we're going to really dwell on this part of Newton's laws. But without any further ado, what I'll do is I just want to go through the laws first, and then we'll start on the application of Newton's second law. Just remember, we're coming back to this part now. And then we've got Newton's third law. Right, now what does Newton's third law state? It simply says if body A exerts a force on body B, then body B will exert an equal but opposite force on body A. Now, I like stating it that way. Of course, I know that there are other ways of stating Newton's third law, but I like that one because what it simply does is that it just makes it that much more clear, right? Simply says if body A exerts a force on body B, then body B will exert an equal but opposite force on A. Now, suppose we're talking about, I know every time I state this, people think, I'm talking something that is not true. There's Africa there. Okay, so suppose this is planet Earth. The Earth is always pulling us towards its center, right? Okay, we're gonna get to that when we do Newton's law of gravitational what do they call that? Universal gravitation. Yeah. So if you think about it, so the Earth is pulling us towards its center, right? But if Newton's third law is to be correct, it means the same force that the Earth exerts on a body of mass, right, will be the same force that the body of mass exerts on the Earth, right? It means as much as the Earth is pulling you, you are also pulling the Earth. I know some of you are thinking, that is very true. So if body A exerts a force on body B, then body B will exert an equal but opposite force on body A. Please, I want you to note, this has to do with a contact between two things, all right? So, yeah, I don't know if I want to make this example. So whenever they say something like, if a force, someone exerts a force on a wall, right? So here's a person, okay, is pushing a wall. All right, you can tell my drawing is absolutely gorgeous. It's excellent stuff. Right, so let's say this person is pushing against a wall, right? What is the action-reaction pair in this case between, now note, the hand and the wall, right? If the wall exerts a force, if the hand exerts a force on the wall, then the wall exerts an equal but opposite force on the hand. So essentially, Newton's third law is an action-reaction type of law, okay? So it means that for every action, there's an equal but opposite reaction. But please remember, you can't now say the reaction pair between the hand and the wall is the person on the is the wall on the person. Remember, if A on B, then B on A. So it's the hand on the wall, right? And then what's the reaction pair? It's wall on the hand. Okay, so in that case, I want us to start now applying Newton's second law. I hope the three laws have been, I've kind of made them as clear as possible. So now I want us to quickly just look at the applications on Newton's second law. Are you ready? All right, awesome. Right, Newton's second law. Now, suppose that we've got a body, all right, a body of mass. Let's say we've got a trolley, okay, and we are going to exert a force on it, okay. let's apply a force there, a force of F. And then let's just say, for argument's sake, it's on a smooth surface. So it means that there's no friction. We're going to talk about friction in just a little while. Right, now, if you think about it, you know what? Let's just put in values whilst we're at it. Let's say it's a 10 kg trolley, right? And we are applying a 40 Newton force, right? Now, first of all, what I want us to do is, first, let's draw a free body diagram showing us all the forces that are acting on this trolley, right? So, a free body diagram showing us all the forces. Now, when you draw a free body diagram, the first thing is that you are going to draw for me a fat dot there, right? And I'll tell you why we want to draw that dot as big as possible. Well, not too big now, right? So what are the forces that are there? So we've got the force applied. Now please just make it a point that when they ask you to draw a labeled free body diagram, you must actually write it out in full, or otherwise, if you decide to call this F, just write there at the bottom, F is force applied, something like that. Okay, and then and then what other force do we have? Of course, gravity is pulling it towards its center, or rather the earth is pulling it towards its center. So this is going to be the force of gravity. Of course, some of you prefer to use weight. Okay, all right, so this is the weight of the object. And then obviously it's actually sitting on a surface, and in this case, what's happening, it means that there will be a normal force, right? There will be a normal force that acts on this body. So here's my normal force. Right, now I want you to note something. We've got two types or two dimensions of forces that we have here, right? We've got forces that are acting vertically, right? And in this case, it's going to be the normal force and its gravitational force, right, or the weight. And we also have forces that are acting horizontally. Now, ladies and gents, I want you to please remember this and know this even for the future. When you get to varsity, it doesn't matter, right? So what is net force? Net force is simply the sum of forces. However, when you take the sum of forces, you only take the sum of forces in a particular dimension. So it means I cannot add forces that are vertical with forces that are horizontal. Okay? So I only take forces in a particular dimension. Are you with me now? Right. So now, let's say, now that we've drawn the free body diagram, now let's do the following. Let's calculate let's calculate the value of our normal force, right? So if I wanted to find out what is the value of my normal force, now I want you to note, I'm looking at, so F net is equals to MA. Okay, right, there's a reason I'm starting here. So in this case, F net is equals to MA, so that you understand in future why I do what I do. Right, now I want you to tell me, when we look at this object vertically, if we are pulling it to the right, of course it's going to move to the right, isn't it? Right? So if we look at its vertical motion, what is it doing vertically? Right? Of course, it's stationary, right? Vertically, it is not moving. So what does that mean? It means that it is not accelerating. You remember Newton's first law, right? So therefore, it means that the sum of our forces in the y direction, in the vertical dimension, okay, is equal to what? The acceleration there would be 0. So as a result, it means the sum of my vertical forces is 0. Okay, right. This is going to help us going forward, so that you understand when we now calculate frictional force when given the coefficient, why we always do this. Now, it means that the sum of my vertical forces is going to be equal to 0. Now, please remember that force is a vector quantity, meaning that force can be measured in both magnitude and direction, right? It's quantified in terms of its magnitude and direction. So as a result, you need to now have a direction. So I'm going to take, for my vertical dimension, I'm going to take upwards as positive. This is just for the vertical, right? So what does that mean? It means my normal force, okay, would be positive, plus, remember we said it's sum of forces, right? Plus, in this case, another force, which is gravitational force. And by the way, gravitational force is acting vertically downwards. So as a result, because I've chosen up to be positive, it means downwards would be negative. So this is minus the force of gravity, right? And this is equal to 0. Okay, right. Remember, what am I trying to do? I'm trying to find out what is the value of my normal force. Sorry that I didn't write that down. Now, therefore, remember in maths, positive times a negative will give me a negative. So what that means is that normal force minus the force of gravity will be equal to 0. So as a result, it means that the normal force is equal to the force of gravity. So I hope you can actually see that. But how do we calculate gravity? All right, for those of you who haven't gone through the section just yet, just please remember that when you calculate force of gravity, it's always going to be the mass multiplied by gravitational acceleration. And this value, we take it as 9.8 meters per second squared. We won't put the SI units just yet when we substitute. So what's my mass? My mass is 10 kilograms, and my gravitational acceleration, that's going to be 9.8, and so this is going to give us 98 newtons. So it means your gravitational force will be 98 newtons, but note this, the sum of forces is equals to 0, so it means that my normal force, because you've got only two forces acting vertically, so it means that the normal force will also be 98 newtons. Okay, great stuff. Now, what I want us to do quickly is now let's calculate the acceleration of this body as it moves horizontally. Okay, so we're going to say, all right, now here's our body. Horizontally, what are the forces that are acting? It's going to be only the force applied, isn't it? So we're going to say, according to Newton's second law, we know that F net is equals to ma, right? I'm going to write it just here. So F net is equal to mass times acceleration, right? But what are the forces that are acting? Remember, I said to you, we only add forces that are in the same dimension. So as a result, F net is equals to ma. So I'm going to say the sum of forces in the x direction, horizontal dimension, isn't it? Right? This is equal to ma, but I want you to note, so what is the sum of my forces? It's only, I'm going to take direction to the right as positive, right? So as a result, what happens? I know that there's only one force there. It's going to be force applied, which is equal to ma. I'm just dragging this now, okay, so that you can see there's no other force that is acting horizontally. So as a result, that's going to be 40 newtons, a positive force, because I've taken that direction to be positive. So that's 40 is equal to, my mass is 10, and I want the acceleration. Of course, we're going to divide both sides by 10 there, okay? And as a result, my acceleration would be 40 divided by 10, which is positive 4 meters per second squared. Please remember the fact that it's positive, it's telling you that it is accelerating in that positive direction there. Okay, right, I hope that makes sense. Right, quickly, I want us to take a similar question, but now what I want us to do is let's assume that there's friction. Okay, so same question again, right? We're pulling with the 40 Newton force, right? But now there's friction. It's a rough surface, right? So it's a 10 kg mass, okay? Right. Now, ladies and gents, I think what I want us to do very quickly, maybe let me just get to the part where we talk about friction before I tackle this question. Now, essentially, I know there are these difficult definitions. We define friction as a force that opposes the motion of an object, okay, and it acts parallel to the surface. Remember, that's the general definition of friction. But you've got two types of friction, okay? Right, you've got what we call static friction, all right? So what happens? Assume that, let's say, this body was stationary, okay? So what would normally happen is that you find that when you try to pull it, it kind of resists, okay? So what's happening? So the static friction is it's a force that opposes the tendency of an object. So it tends to want to go. Some of you who've pushed cars before, you'll always realize that it's more difficult to push a car right at the beginning when it's still stationary. But once it starts moving, then it starts flowing. Why is that? Because at the beginning, you are acting against what we call static friction. Okay? So it's a force that opposes the tendency of an object, to want to move, right? And it's always relative to a surface. So in this case, what happens is that the body wants to move, but there's frictional force that's kind of pushing it, pulling it backwards, and as a result, we call that static friction. But now, what happens is that you now start exerting a bigger and a more bigger force and a bigger force, and then eventually, right, you overcome the maximum static friction. All right, so you have to overcome the maximum static friction before the object actually starts moving. All right, now when it starts moving, you hear a sound, right? Where does that sound come from? It comes from the friction between the wheels, or between the object and the surface itself. And we say, what is kinetic friction? It's a force that opposes the motion of a moving object relative to the surface. So essentially, friction opposes motion. Okay? Friction opposes motion. So then that is where we are talking about static friction. Okay? Now, how do we calculate friction? Let's say, for instance, all right, you were given that this is a rough surface. Okay? So when they normally, what they do, or what may be given, is what we call the coefficient of friction. So if it's a static object, obviously it will be mu s, right? In this case, mu is a Greek symbol, right? It's a Greek symbol u in a sense. So mu k, in this case, this is what we call the the coefficient of friction. So we call this the coefficient of friction. All right, we call this friction coefficient. Right? So in this case, what we say friction coefficient is, it will be the ratio between, right? And I want you to please note, the frictional force, okay, and the normal force acting on a body, right? So essentially, this is what the coefficient of friction is. Now, let me put it in a very simple or simplistic way. The coefficient of friction is the roughness of the surface. So if you think about it, if you're using ceramic tiles, right, and let's say a tarred road, okay, which one has a rougher surface? Okay, obviously the ceramic tiles are more smoother, right? than the tarred road, isn't it? So all you're simply saying to me is that the coefficient of friction that is on a tarred surface, right, is greater than the coefficient of friction on ceramic tiles. Essentially, hey, clever you, yes. Okay, right. So in this case, how we calculate friction, we say friction, right? If we put this another way, will be the coefficient multiplied by the normal force. Now, in this case, if it's a moving object, obviously it will be kinetic friction. If it was a stationary object, obviously we would use the symbol Fs, which is mu s multiplied by the normal force. So essentially what we're simply saying is that how you calculate friction, you need the normal force. I think now you can see why I was showing you what I was showing you before, right? Okay, so in this case, we've already calculated the normal force. I showed you how, isn't it? Right, so the first thing is, let's calculate the value of friction. So calculate friction, okay, the value of friction. So how are we going to get that value? So we're going to simply say kinetic friction. I'm assuming that this body is already moving, right? So it's going to be mu k multiplied by normal force. Let's say they give us a coefficient of friction to be 0.2. Okay, right, and please remember, because it's a ratio of forces, that's why it does not have SI units, right? So in this case, we're simply saying that the coefficient is 0.2, and our normal force, remember we calculated the normal force for a 10 kg object, so we say that is going to be 98 newtons, right? So as a result, we say 0.2. Let's get our calculator out. All right, and then we're just simply going to say the 0.2 multiplied by 98, and you get 19.6. So I get a value of friction to be 19.6 newtons. Are we together? Okay, I hope that you're still okay. Now, the part that I really wanted to get to was now the calculation, right? So now, secondly, I want us to calculate the acceleration, okay? Right. So how are we going to get the acceleration of the object? Let me just move that a little bit. Right, so how are we going to get that acceleration? Well, you guessed it. So now we know F net is equals to ma. Now, which forces are we going to take? You're quite right. Because this object is moving horizontally, right? So it means that it will be the sum of what? Of my horizontal forces, the sum of my forces in the x direction, because it is accelerating in the x direction. So as a result, once again, remember, I've chosen upwards as positive, right? Sorry, not upwards, rather the direction to the right as my positive direction. So in this case, it will be what? The force applied, okay, plus a negative friction. Notice, okay, so I actually should have indicated there. So what are the forces that are now acting on this body, right? It means it will be the force that is now being applied. Okay, so that's force applied, right? I'm going to just abbreviate that, right? And then what else do you have? You have frictional force. Remember we said friction opposes the motion of an object. So in this case, if I'm going to the right, then friction would tend to oppose the motion. So this would be the value of my frictional force. And obviously we'll have those other two forces, which is the force of gravity or the weight, okay, as well as the normal force. Now, if you think about it, we're just looking at forces that are acting horizontally. So we said it's going to be the force applied, there it is there, right, plus a minus. Remember we said right is positive, so it means that friction is acting in the opposite direction. So minus friction, and this would be equal to MA. Now let's substitute our forces. So we know this is going to be 40 newtons, right? So this is minus positive and a negative. So that's minus 19.6. And this is equal to 10A. Okay, right. So can do that calculation yourself. 40 minus 19.6. Okay, and you get that value. Then you divide it by 10, and there it is. There we've got acceleration is 2.04 meters per second squared. Okay, now yeah, let me just lift that a little bit. So now if you think about it, it's the same object. All that we did now, initially it was moving at it was accelerating, meaning it was increasing its motion, okay, its velocity every second by 4 meters per second. Okay, right? But now all of a sudden the acceleration has been reduced. And why is that? All of a sudden because we had friction that was opposing the motion of the object. All right, I hope that makes sense. And what I want us to do now, I know that some of you are thinking, but I know they're not going to give us questions like those, something that is as easy as that. Don't worry, we're getting to that part. Okay, so we're going to be tackling past exam questions, all right? And I want us to look, but before we get into that, remember here we were just looking at a scenario where we had forces that are acting horizontally. Well, of course we had forces that were acting vertically, but the motion was actually vertical motion, right? Horizontal motion rather. So what I want us to do is to quickly look at vertical motion. Okay, right. So suppose we had a block, all right? Okay. Yeah, let's just say 5 kilogram block. Okay, and we are, look, we're pulling this up. Let's just say for argument's sake, we're going to be pulling this block up with an, okay, let's say an 80 Newton force. Okay, right, so here it is. We've got a block that is being pulled upwards, okay, with an 80 Newton force. Okay, right, and we want to find out, right, first of all we want to draw a free body diagram. So draw a labeled free body, if you don't mind, diagram. Oh, and by the way, there's a difference between a free body diagram, right, and a force diagram. Remember, when you draw a free body diagram, right, you are going to use that dot there. That's the dot that we're talking about. And by the way, what that dot symbolizes is what we call the center of gravity. For those of you who will do mechanics, either, you know, as you pursue physics further, whether in engineering or other science related courses, you'll start to talk about the center of gravity or the center of mass, okay, of an object. So in this case, what this shows us, this dot tells us about the center of gravity, right? So what are the forces that are acting? We know we have the force applied, so we are pulling this object upwards, right? And what other force do we have? Now think about it. As you are pulling it up, gravity is saying, "Hoi, come back." All right, so the force of gravity, so we said, let's write that out in full. Right, so the force of gravity is pulling that down. Now, ladies and gents, I just made a mistake here. That's why I hesitated a little bit. So try as much as possible to show So when I look at your diagram, I must be able to see that the force, I can already tell that the force that is applied will be greater than the gravitational force. So try to have the length of your lines kind of tell that story. Okay, so I'm sorry I made that mistake there, but I was actually trying to rather elongate that line so that you can actually see that this force here is bigger than this force. So in a sense, your free body diagram should tell a story to some extent. Okay, of course, for those of you who are doing matric, they're not really going to penalize you if you don't show that. But what really does matter is that these lines here are connected to the dot. So you can't just draw a line, let's say here's your dot here, and then you draw the force like this. Okay, right, so it must be connected to the dot. And then secondly, also you must show the direction. I've seen some of my students give me something like this, and then they'll say this is force applied, and then this is gravitational force or the weight. Right, please remember you must show, because arrows actually show the direction of the force. Okay, right, now let's talk about, or rather let's calculate the acceleration. So now we want to calculate acceleration. Okay, acceleration. Alrighty. Okay, so how are we going to get the acceleration for that guy? Right, so now we know there's a force going upwards, and by the way, now that this object is suspended, so once you lift something up, it is no longer on the ground, isn't it? Right, so therefore there is no normal force that acts on that particular object. So I want you to please note, normal force will only be there when an object sits on a surface. So if an object is actually in contact with a certain surface, all right, so in this particular case we will not have what do we call it, we won't have the normal force. Right, now let's talk about the calculation for the acceleration. So now, once again, I am going to assume that the direction of motion is positive. Now please note, I've already noticed, okay, that my gravitational force, right, let's calculate gravitational force there. That's mg, so that's going to be 5 times 9,8, right, 9.8. So that will give us 49 newtons. Okay, so now I can see that obviously 80 newtons is much greater than 49. So who's winning? It's going to definitely be the applied force. So as a result, where's my net force? Which force is going to win the battle? Of course, it's going to be my applied force. So as a result, this thing will tend to move upwards. Okay, right, so now I'm going to say, okay, take direction upwards. So I'm taking the direction of motion as positive, right? So I'm going to simply say F net is equal to ma, but what is my F net? So that's going to be the force applied, okay, so force applied, okay, plus a minus. By the way, there's nothing wrong if you just simply said force applied minus gravitational force, right? So I'm just trying to show that part that F net is the sum of forces, right? So a sum you usually add. So that's minus gravitational force, or minus the weight, and this is equal to ma. So what is our force applied? That's going to be 80, okay, minus 49, and this is equal to the mass is 5, and we wanted to find what the acceleration is, right? So let's put that in our calculators, right? So that's 80 minus 49, okay, that should give us 31, okay, so that's 80 minus 49, that gives us 31, and we divide that by 5. Okay, I get a value of 6.2. So you got 31 and you divided both sides by 5. Okay, and your acceleration should be equal to 6.2 meters per second squared. Note once again, your acceleration came out as positive. So what does that mean? It means this body was going towards the right. Okay, right. I hope that helps. Okay, I hope that can be understood perfectly. Okay, now let's move on to kind of more complex problems, right? And in this case, we're going to be just quickly looking at problems where you've got more than one part in a system. Okay, right. So I want us to look at one such example. Okay, suppose we've got, let's say, on a rough surface there. Okay, let's say we're going to pull these two objects. Let's say the mass of the one is 10 kilograms. The mass of the other one is 5 kilograms. Okay, and you know what, so that I don't create the impression that it's always moving to the right, let's pull this one here. Okay, right, now let's apply a force. Okay, right, so what I want us to do, let's say the coefficient of friction, let's call this X, let's call this Y. So we've got two trolleys that are attached by a string. Right, now I want you to please note, normally the examiner likes using certain words, and there's a reason why they use those words. So they would say something like a light inextensible string. Right, there's a reason why they are using those words, because first of all, if it's a light string, then it means its mass will not contribute to the mass of the entire system. Okay, and then they say inextensible. What does that mean? Right, so it means that it's a string that you cannot extend, you know, like a rubber band, something like that. Now the reason why they want to say that is, if it's an inextensible string and the tension is maximum there, right? So what it means is that as I pull the 5 kg mass, right, automatically whatever this guy is doing, this one will begin to do as well. So it means if this one is accelerating at, let's say, 1 meter per second squared, so it means that the 10 kilogram mass will also accelerate at 1 meter per second squared, right? So essentially, inextensible simply says to us, whatever the one does, the other one also does. So the acceleration of the system should be the same. Okay, now if you think about it, if you are using a rubber band, you know, it's possible that whilst I'm pulling this one, the band is still kind of stretching there and this one is still stationary. Okay, so we want to avoid such a situation, because can you imagine how complex it would actually make our problems to be. So now what we want to do is want to see how do we tackle a problem like this. Okay, right, so let's say, just for argument's sake, we are going to apply a force. All right, let's just say this is 100 newtons. All right, so we're going to apply 100 newtons of force, and then let's say the coefficient of friction on X. So coefficient of friction on X, let's just say for argument's sake is 0.2. Let's say the coefficient of friction on Y is 0.3. Okay, right, I'm just thumb sucking those values. Okay, Don't think they come from some empirical you know it's empirical data that comes from somewhere. No, no, no. I'm just thumb sucking those values. Okay, right. So now there are several things that I want us to do. Okay, so first of all, I want us to draw a free body diagram, right? So we're going to draw a free body diagram. Okay. So let's draw a free body diagram for X. Okay, so this is for body X. And then what we're going to do is we are going to just calculate friction for both systems. So let's calculate the friction so let's calculate frictional force, calculate kinetic friction for X, okay, for X and Y. Okay, right. I know that's not a standard way that they're going to put it. We're going to deal with past exam questions. Don't worry. I just want you to grab the concept on this video. And then thirdly, what I want us to then do is to now calculate, okay, let's say 3.1, the acceleration, and for 3.2 we're going to calculate the tension on the string. Okay, so what we're simply doing is that we want to look at all of those questions for this particular system. All right, are you ready? Are you sure you're ready? Okay, right, now let's go. Okay, so first of all, let's draw a free body diagram for X. Now you're going to be helping me out. So what are the forces that we have on body X, right? You're quite right. So we have an applied force. Okay, so we've got an applied force, so there's our applied force there. Okay, and then we also have gravitational force, or the weight. So that's the force of gravity. Okay, and then you're quite right, the normal force. I know you are guessing all of them quite correctly. So I've got the normal force there. Now, why do we have the normal force featured on this one? Obviously because it's sitting on a surface, isn't it? Right, and then you can almost agree with me. As I pull this thing to the left, what's happening? Obviously, I'm going to experience friction in the opposite direction. So I have friction opposing the motion there. So that's going to be frictional force. You see, I'm writing out the words in full so that my examiner knows that I know exactly what I'm talking about. And then what do we have? Now, please, I want you to note. Remember that these two trolleys are attached by that string there. Now, I want you to just imagine, okay? As I'm pulling this trolley, if I were to suddenly cut that rope there, what do you think would happen to block X? Yeah, it would actually tend to accelerate even more, right? It would move even faster. Why? Because as it's attached with this string here, this guy is kind of slowing this trolley here down. Can you see? So there's a tension that is acting on the string, and that tension is actually slowing that trolley down. Now, some of you might ask me, but how do you know whether the tension will be bigger than the frictional force? Actually, I don't, okay? But it's just an assumption that I'm making, right? As I said to you, the examiner will not necessarily be very strict about those issues because at the moment, obviously, we don't have any values, okay, attached to that, okay? Right, now, what I want to do whilst I'm at it. Okay, let me just create some space here. So what I want to do whilst I'm at it, do you mind? Look, I know we were not asked for it, but what I'm going to do quickly is let me draw a free body diagram for body Y as well. Okay, right. So let me draw a free body diagram for body Y. So what are the forces acting on body Y whilst we're still talking about this free body diagram thing, right? So what are the forces acting on it? Of course, that's going to be the force of gravity. You're quite right. If you don't mind, let me call this force of gravity X. All right, and then let's call this one force of gravity Y. Okay, yeah, I don't know how to, of course there's that Y there. Okay, and then we've got the normal force. Okay, so that's the normal force. Okay, of course that's normal force on Y. And then what's happening on body Y? Right, if you had to cut that rope, obviously it would body Y would not be able to move, isn't it? So it means what's causing body Y to move? It's not that force there, it's the tension here, right? So essentially we know there's a tension that is experienced in that direction. So there's our tension for body Y, right? Acting on body Y. And by the way, I want you to please note it's the same rope, isn't it? Right. If you kind of remember, if body X exerts a force on body Y exerts an equal but opposite force on X. And what is the attachment between the two? It's that tension there. So it should be the same tension. Okay. Right. So in this case, there's friction. Okay. Remember, it's opposing the motion. So this is the friction. This is friction X. This is friction Y. Okay, awesome stuff. Right, now the second question. They said to us, okay, right, remember the answer to this question is this one. And normally, ladies and gents, can I just help you to notice this? When the examiner asks you to draw a free body diagram, you'll realize that they'll always give you a mark allocation, right? And the mark allocation is always it always corresponds to the number of forces that you are going to have on your system. So if it's a 5-mark question, so typically this would have been out of 5 marks. Okay, why is that? Because there are 5 forces that I was going to draw. Okay, so kind of note that, and you'll see that as we do past exam questions. Right, now let's look at it quickly. So now we want to calculate frictional force for this guy. Okay, so we're going to say, all right, how do we get the value for friction? Okay, so we're going to say, but we know that friction, okay, so this is for number 2. We know that friction, okay, we're assuming it's moving. So friction, that's going to be friction coefficient multiplied by the normal force. Okay, but remember, you remember when we did our initial question, right, where we had that normal force. Now in this case, once again, right, we're going to our vertical forces. I think you get it by now, né? So we're looking at our vertical forces. What are the vertical forces, right? The sum of my vertical forces is equal to 0 because I'm assuming that it is not moving vertically. There's nothing that we've been told about that, right? So then that means that the normal force minus the force of gravity is equal to 0. So therefore, normal force must therefore be equal to the force of gravity, and which once again, that's 5 times 9,8. And if you remember, we got 49 newtons from that, right? So essentially, what I'm simply saying is that that value for friction is simply going to be, right? Now remember, the coefficient of friction of X, that's 0.2. What is my normal force, right? They gave me the normal force now, not they gave me, rather, we calculated normal force to be 49, and in this case we say 0.2 multiplied by 49. I think we had used that value before, right? Oh no, it was 0.2 times 98, so we get a value here of 9.8 newtons. Now please don't mistake this for the 9.8 for gravitational acceleration. Okay, so this 9.8 newtons is just the friction that's acting on this guy here. Okay, right. If you want to, okay, so let's try and create some space here. Right, so if you want to, what we'll do is we will also calculate the friction. We're gonna need it anyway, right? Let's calculate. So this is frictional force on X, so frictional force on Y. Okay, so this is FKY. This is going to be the coefficient. Remember the coefficient, okay, is 0.3, so that's 0.3 multiplied by the normal force for this guy. Okay, so once again, normal force would be equal to gravitational force. Remember, it's a 10 kg block, so this is mass, that's 10 times 9.8. okay, so we have 0.3 times 10 times 9.8. okay, and I get 29.4 newtons. Okay, please, fellow scientists, I know you know how important it is for us to always have those SI units. All right, now, ladies and gents, let's get to the crux of the issue. Right, now we want to calculate the acceleration. So now I know that there is a way in which we can actually take the system in its entirety, to take this as one system. But you know what? I would rather teach you this. It's a very systematic approach, okay? Of course, there are other ways in which you can do it, but I want something that is going to be foolproof, that's not going to cause you to have more questions, right? So let's do this. Let's take one part at a time. So let's start with trolley X, right? So now what are the forces? So we're going to say for trolley, this is for trolley X. Okay, so for trolley X, right, what are the forces that are acting? Right, so we're going to say F net is equal to MA, right? Now, what is my net force? Remember, it is accelerating horizontally. You remember that, right? So it's accelerating horizontally. So the sum of my horizontal forces. Now, what are my horizontal forces? It's going to be the force applied. It's going to be the tension. It's going to be the frictional force on X. Now, remember, ladies and gents, that when I'm looking at these, right? So for this trolley, I'm taking the sum of forces where? In the X direction. And this is equal to MA. Now, which are those forces? So sum of forces in the X direction, I'm going to consider going to the left as positive. Remember, I said to you direction of motion, right? I regard it as positive. I'm assuming that it's accelerating in that direction. There's an applied force there. And by the way, it isn't to say that the direction of the applied force will always determine where the system is going, right? It just depends on the question. But in this case, I'm assuming that it is going to be moving in that direction, right? So I'm going to say sum of forces. So it's going to be that force applied minus the tension, that's minus the frictional force on X, and this is equal to MA. Now note, what is my force applied? That's 100 newtons minus the tension. We don't know what the tension is on the string, minus the frictional force on X. You said that's 9.8, and this is equal to, what's the mass? That's 5, and the acceleration is unknown. Okay, so I have 100, so these are like terms. 100 minus 9.8, so 100 minus that 9.8 value, right? You have 90.2, right? So this is 90.2 minus t is equals to 5a, and I'm going to leave that as equation 1. Okay, right. Oof, I might run out of space, but don't worry, we'll make a plan about that. Right, so in this case, I'm simply going to leave that as equation 1, right? And then let's take now, where are we going to, we can't solve this any further. Why? We've got t and a as a variable, so I need another equation. So I'm going to take for equation for trolley y. Okay, right, so let's take for trolley y. Now, what are the forces acting on trolley y? The horizontal forces, right? It's going to be the tension acting in that direction. Remember, assume that going to the left is positive. So it means for trolley y, the sum of forces in the x direction is equal to ma. Once again, that's going to be tension, positive, right? Okay, notice the tension was negative for this one here because it was opposing, right? But the tension is positive for trolley X because it's the one that's pulling it, that's propelling it forward. So that's tension minus the frictional force on Y. You remember we got that value for frictional force on Y. That's 29.4, right? And this is equal to, the mass is 10 and the acceleration is acceleration A, right? Now, please, I want you to note this. So this is going to be t minus 29. Oh, by the way, we can't solve any further once again. Sorry about that. So we call this equation 2. Okay, right. Yeah, let's just bring that there. Okay. Now, ladies and gents, we find ourselves with a little bit of a predicament. Well, it's a little bit of a predicament. It's not really much. Right, so I just want to grab something here so that I can continue on the problem that we are doing. Right, so we find ourselves with a little bit of a predicament, right? So in this case, we cannot solve both of those equations. So what are we going to do to try and solve that problem? So if you don't mind, I'm just going to continue over this side. Now, I know some of you prefer to simply say, okay, I'm going to take t as the subject of the formula and so on and so forth. I like doing the following. Now, please, I want you to follow me in what I'm going to do just now. Right? So I've got those two equations, 90.2 minus t, which is equals to 5a. We said that's equation 1, right? And then we've got t minus 29.4 is equals to 10a. I call that equation 2. So now all I'm simply going to do, please, I want you to watch this carefully. I'm going to take equation 1 plus equation 2. Okay? Right. So to solve it, remember I'm still looking for my acceleration, right? So I'm going to take everything that's on the left-hand side of each equation and sum it up. So that's 90.2 minus t plus, right? So that's everything on this equation. Now I'm adding it. Remember I said plus, I'm adding it to everything that's on the left-hand side of my second equation plus t minus 29.4, right? And what is this equal to, right? So now I'm adding everything that's on the right-hand side. On the right-hand side, what do I have? I have 5a, that's 5a plus 10a. Now, I can hear someone wanting to jump up and say, yeah, but why didn't you consider the system as one thing in the first place? Look, you can't do that, okay? There's nothing wrong with that. Just look at all the external forces. That would have been 100 and the two frictions for the thing, okay? And then you take the sum of the masses of the system. Okay, it's just that teaching it this way will ensure that even whatever variations there are, you can still answer the question. Okay, right, now please remember we added on both sides, so that's 90.2 minus t plus t minus 29.4, and this is equal to, we added the right hand side, 5a plus 10a. Now notice what happens. If you do this correctly, you'll always get rid of one of your variables. Minus t plus t, of course, those actually give you 0, right? So those cancel out. So now what do you have? 90.2 minus 29.4 minus 29.4. Okay, so we've got 60.8, which is equal to 5a plus 10a. Those are like terms, so I can add those two. That's 15a, and of course we're going to divide both sides by 15. Okay, so divide by 15, and I get an acceleration of 4.05 meters per second squared. Okay, right, I hope that makes sense. All right, so all we simply did is to take the sum of forces for trolley X, we got that equation. Take the sum of forces for trolley Y, we got that equation. We summed up the two equations and we got the acceleration. Now, for the last question, they said to us we need to calculate the tension on the string. Obviously, to get the tension on the string, this was question 3.2, right? To get the tension on the string, what are we going to do, right? We simply are going to take one of the equations, and it doesn't matter which one rather, you should be able to get the same answer, right? Let me take equation 2. So what I'm going to do is I'm going to substitute for the acceleration, which is 4.05, okay, meters per second squared, in equation 2. Okay, so it means t minus 29.4 is equal to 10 times, what is my acceleration a there, right? We said it's 4.05. So okay, times 10. Okay, so here we get 40.5. all right, so t minus 29.4 is equals to 44.5. if I take that to the other side, so this is plus 29.4. okay, right, and I get, okay, that's going to be 69.9 meters per second. Sorry, this is tension, so that's a force that should be measured in newtons. Okay, I hope you can you understood that question, right? Sorry that we ran out of space. Okay, so this is how we tackled it. We found the friction there. Okay, the friction for trolley X, we found the friction for trolley Y, and then we simply calculated using Newton's second law, right? So that's force applied minus tension minus friction, and so that's why it's always important for you to draw that free body diagram. Okay, great stuff. If I'd like for you to actually try out this problem on your own, so that you can be able to try and solve as many of them as possible, so that you verify that you get to the same answer. And please throw some comments if you need more clarity on it. You're more than welcome to just send a question directly to me, right? I did give you my email address right at the beginning. Okay, Right, so we continue. Right, let's take a system whereby we are looking at horizontal motion, rather vertical motion. And I think what I want to do is I'm gonna leave this. I'm actually going to do this as the last question, and then in our next video, what we're going to be now tackling is going to be the forces when there's a pulley in between, or systems whereby there is a pulley and you find maybe one moving horizontally, another vertical. But we'll take that in stride. Okay, so right, let's look at it quickly. So we've got a force, sorry about that little error there. Right, so we've got a force of 460 newtons, right, acting on an object. Okay, all right, pulling objects upwards. All right, so the two objects are actually attached by a string. Remember, we said it's a light inextensible string. And in this case, we want to calculate the acceleration as well as the tension. Right, so what I want us to do quickly is let's now determine, let's draw the free body diagram quickly. So here it is. Let's draw a free body diagram. If you don't mind, let's label them. Let's call this A. Let's call that B. So I'm going to draw a free body diagram for A, right? What is it going to look like? It's going to have an applied force there, force applied, okay? And what else? Remember, it's going to be a tension, okay? Right, and now this is the reason why I was saying that you need to draw a big dot, right? Because sometimes you find more than one force acting in the same direction. And what I've noticed, some of you, have a tendency of, drawing this small dot and then you'll do something like this. You'll say this is tension and then you say force of gravity, right? Notice, do you see that once I do this, I've now changed the direction of the force of gravity, right? So please, this is incorrect. So instead, what you simply do, just draw that dot to be big enough for you to accommodate both forces in the same direction, right? So I'm going to say this is going to be the weight of the object. Okay, so this is the weight on A. Okay, and then there's our free body diagram. So that's the free body diagram on A, right? And then if you don't mind, let's rather do this. Let's make an equation. All right, let's make an equation for A. Okay, so it means if I take upwards as positive, I'm assuming that I'm pulling it up. I'm assuming that it's gonna go up. Right, so F net is equals to MA. Please note in this case, my forces, I only have vertical forces. So in this case, of course, I'm taking the sum of forces in the vertical, right? So the sum of forces in the vertical, what is that? That's going to give me MA. So this is going to be what? Force applied minus the tension minus the weight of this object. And what's the weight? That's going to be 10 times 9.8, okay, is equals to what's the mass of A? That's 10, and the acceleration is A. Okay, so I've got force applied, let me just leave it as FA, minus tension, my force applied value actually is 460. Yeah, that's what I wanted to do. Okay, let me just erase that there. So this is 460 minus tension minus 98, and this is 10A. Okay, Right, so my like terms, I'm going to continue over to the other side. Right, so my like terms, okay, so I'm going to say 460 minus, okay, so there's that 460 there. Okay, so that's 460 minus the 98. Okay, so that's 460 minus 98. That's 362. Okay, so I get, right, sorry, I'm just going to take that down there. So that's 362 minus the tension, which is equal to my mass is 10. That's 10A. Okay, right, so that's going to be my equation 1. Agree? Right, and then I am going to now go, obviously I can't solve any further. So what do? I go for this one here. So what are the forces acting on the 20 kg mass? Obviously, if it's attached there by that string, right, this string would be the one that is actually pulling the 20 kg mass upwards, isn't it? So as a result, the same tension. So tension, and what other force? It's going to be, oh man, my drawings are really disappointing. So that force there, that tension, should be actually bigger than the force of gravity, or the weight. Okay, right, so now what do I know in this case? I know that F net is equals to MA once again. That's the sum of my vertical forces. Okay, right, is equals to MA. So that's T, right, upwards, minus the weight for the 20 kg, remember? So that's 20 times 9.8. And this is equal to the mass is 20 and the acceleration is A. Okay, right, so that's T minus 196, that's 20 times 9.8, and this is equals to 20A, and this will call equation 2. Now, as I said, ladies and gents, it really makes it easy. If you had decided to take this as force applied, and thereafter you just took the weight of the entire system, absolutely nothing wrong with that. Okay, right, but as I said, I want to take this approach so that I'm consistent. Even when I start introducing other things, then you are able to follow quite well. Okay, right, now look at this. So I've got T minus 196 is equals to 20A. So this is now I'm going to take the sum of equation 1 plus equation 2. So everything on the left hand side of each equation, right, remember my first equation, that's 460 minus T plus, okay, no, sorry, that's not 460 minus T, sorry, remember it's this one here, that was my equation 1. So that's 362 minus T plus 19, plus T. See, I'm making a lot of errors. Okay, I'll just cancel that so that it doesn't look clumsy. Right, so that's 362 minus T plus T minus 196. Okay, this is equals to what? 10A plus 20A, which will give us 30A. As I said, if you generated the equations in the correct way, you'll always get rid of the variables minus T and T. Okay, right, now if you don't get this, your variables cancelling, what you simply do, it simply means that there's something that you might have done wrong. Okay, so just go back to your equations, and try to fix what you might have done wrong. Okay, right, so let's say 362 minus 196. Okay, I get 166 and I divide that by 30. Okay. All right, remember you're going to divide everything by 30. So this minus this, divide by 30. Okay, so my acceleration is 5.53 meters per second squared. Okay, right, sorry about that. So that's 5.53 meters per second squared. Ladies and gents, I think at this rate, yeah, of course, I didn't do questions whereby you find that you've got, just other permutations, maybe something like you had the force missing, or yeah, something like that. They've given you the acceleration, or they tell you about constant motion and all and so on. I'd rather tackle that in our next session. But for now, what I wanted you to just grab is just how to tackle those questions on Newton's laws. I really hope, ladies and gents, together with the theory that we've done, okay, that it's been really helpful. As I said, if there are any teachers or parents watching this, and you maybe want to comment, or you maybe have questions, or whatever the case may be, you're more than welcome to do so. And by the way, you are also welcome to get in touch with me on my email address. That's mlungisi.m.nkosi@gmail.com. Right? And some of you have been asking me about also extra classes that we offer. Please, if you are interested, you are more than welcome to also send through a request, and then we will obviously assist you with that. Now, for me, at the end of the day, I want to make sure that I help as many people as I possibly can. I want you to realize that physics is really not something that bad. Okay, I really have gotten some good reviews, and I want to send a shout out to Dudu. She sent an email, and then she followed up with a call. Um, you know, the whole intention of these videos is to try and assist as many of you that are out there as possible. Some of you have had, you've done physics. It's been a while since you've done physics. Some of you are in matric this year. The whole point of it is that anyone can learn physics. It's just the manner in which we teach it, and the manner of approach. But more than just doing the videos, please also supplement with just trying to do as many questions as you possibly can. And you're more than welcome to send me questions. All right, and then if I can, I will also try to answer them here on this platform. Otherwise, for now, thank you, ladies and gents. I think it's really been a productive and awesome session. I'll see you on the next episode of Newton's Laws. It really is one of my favorite sections. And I want you to really realize that just anyone can learn, and anyone can actually master physics. Okay, otherwise, I'll see you again. Sharp, sharp.